on the surface the charges are located. The dielectrics are nothing but non-conducting substances, or we can say they have no charge carriers. They are insulators. In the absence of electric field, we know that polar dielectrics have a permanent dipole moment. The centers of positive and negative charges do not coincide. Hello everyone, welcome to session 5 of chapter 2 Electrostatic Potential and Capacitance. This is Swati, Department of Physics, Vidhyaashram University College, the Temple of Excellence, Mysuru. In this session, we are discussing about the electric field at a surface of a charged conductor. So, we are talking about what is the impact of electric field, what is the expression for electric field at a surface of a charged conductor. So, for this, I have considered a surface of a charged conductor as well as I have considered a cylindrical surface. You can see here the cylinder is partly inside and partly outside, and on this surface the charges are located. And we can also observe the electric field is normal outside the surface since we have considered the positive charges. And in this r cap is a unit vector which gives us the direction of electric field. So here we are going to derive the expression, that is E is equal to, since it is on surface we are doing it is sigma divided by epsilon naught into n cap. So what is sigma in this? It is surface charge density, and n cap is a unit vector which is normal to the surface. So here according to this we have considered a short cylinder of area of cross section, that is delta S, and whatever the surface we have considered here is an imaginary surface, that is a Gaussian surface, and the Gaussian surface we have considered is a cylindrical surface. So inside the surface, as we all know, the electric field is 0, that is E is equal to 0, because inside the surface there is no accumulation of charge and we can say electric field is 0, but outside the electric field is not 0, it is normal to the surface. So it is phi E is equal to E into delta S, that is nothing but the electric flux, that is number of field lines passing through the surface, that is phi E is equal to E into delta X. Why? Because the electric flux is nothing but electric field into the area of cross section. The area of cross section we have is delta S. Now what is the total charge enclosed by the cylinder? We have to find out, that is Q is equal to sigma into delta S from surface charge density, because sigma is equal to Q divided by delta S as we know. So from this we can write Q equals sigma into delta S. Now the Gauss law states that phi A is equal to 1 by epsilon naught times the charge enclosed by any surface, that is phi E is equal to Q divided by epsilon naught. That's my equation 2. So first equation also gives us about an idea, that is phi E, that is electric flux, and here according to Gauss law the electric flux is Q divided by epsilon naught. Now since the LHS is same in both the equation, we can equate them. So from equation 1 and 2 we can write the RHS of the equation E into delta S, and the RHS of the equation 2, that is Q divided by epsilon naught, we get E into delta S is equal to sigma into delta S divided by epsilon naught, because Q is equal to sigma into delta S, and delta S can be cancelled. We remain with E is equal to sigma divided by epsilon naught is the expression for the electric field at the surface of a charged conductor. In vector form we can represent this as vector E is equal to sigma divided by epsilon naught into n cap, where n cap is a unit vector. So this is about electric field at the surface of charged conductor. Now let us move on to a new topic, that is dielectrics and polarization. What is the meaning of dielectrics? Why do we call the substance as dielectrics? So dielectrics are nothing but non-conducting substances, or we can say they have no charge carriers. They are insulators. For example, we have glass and mica and etc. They are non-conducting substances and we call them as dielectrics. What are the types of dielectrics? There are two types of dielectrics. One is polar dielectrics and the other one is non-polar dielectrics. How are they different from each other? What are their characteristics? In polar dielectrics, the center of positive charge and negative charge do not coincide and the molecules have a permanent electric dipole. What is the meaning of permanent electric dipole? Electric dipole means we know it's two equal and opposite charges. They are separated by some distance, that is 2a. We will call it as electric dipole. So here in polar dielectrics, the center of positive charge and negative charge, they do not coincide, which means they are separated. They have some distance or difference between the centers of these two charges, and we call them as polar dielectrics. The molecules do not have a permanent electric dipole moment. What's the example for polar dielectrics? Say for example, we have water, carbon monoxide, hydrochloric acid, etc. In these compounds or in these substances, the centers of positive and negative charges do not coincide because they are separated by certain distance. They have a permanent electric dipole. What are non-polar dielectrics? The centers of positive and negative charges coincides and they do not have any permanent electric dipole, because you can observe here the center of two charges coincides. Dipole means there must be a difference between two charges. In case of non-polar dielectrics, the positive and negative charges centers will coincide and the molecule has no permanent electric dipole moment. The example for non-polar dielectrics are hydrogen, oxygen, carbon dioxide, etc. So from this we have just got an idea what are dielectrics, what are the types, what are polar dielectrics, what are non-polar dielectrics, how are they different from each other. Now let us understand what happens if we place non-polar dielectrics in an electric field. If you place a non-polar dielectric in an electric field, what is the observation? So when a non-polar dielectric is held in an electric field, you can observe here, this is a non-polar dielectric where the centers of positive and negative charges are coincided. So when there is no electric field, this is the condition. So now if the same dielectrics are placed in an electric field, you can observe here, they are separated. Positive charge and negative charge, they are pulled apart. You can observe here, if this is the direction of electric field, I am placing the same non-polar dielectric in an electric field. The centers of positive charges and negative charges getting separated, and the positive charge you can observe here, they are pulled in the direction of the electric field, and the center of negative charge is pulled opposite to the direction of electric field. So this is what the observation when a non-polar dielectric is placed in an electric field. In the absence of electric field, the centers of those two charges are coincided. In the presence of electric field, you can observe the positive charges pulled in the direction of electric field and negative charges are pulled opposite to the direction of electric field. Therefore, we can conclude that when a non-polar dielectric is placed in an electric field, they get polarized, which means there will be a difference in their centers. They will move apart from each other and hence we can create a dipole moment between them and we can say the non-polar dielectric is now polarized. Now let us understand what happens to a polar dielectric is placed in an electric field. In the absence of electric field, we know that polar dielectrics have a permanent dipole moment. The centers of positive and negative charges do not coincide. Now, what happens if the same dielectric is placed in an electric field? When there is no electric field, the behavior of the polar dielectrics, which means they are randomly arranged. You can observe here, the dipoles are oriented in random directions as shown here. So when they are in random motion, we can say the net dipole moment is 0. The total dipole moment is 0. So when the external field is applied, suppose if external field is in this direction, we can observe here the polar dielectrics are arranged or oriented in the direction of electric field, and this results in net dipole moment. Let us now understand one simple concept, that is linear isotropic dielectrics. So when do we say the dielectrics are linearly isotropic? So when the induced dipole moment is in the direction of field. Field means the electric field, and it is also proportional to the field strength, the substances for which this assumption is true. We call them as linear isotropic dielectrics. We can observe non-polar dielectrics now placed in an electric field, and we can create by separating the charges, the center of positive and negative charges. And we know that when a polar dielectrics, they are randomly arranged without electric field. When they are placed in an electric field, we can see that the dipole will be oriented along the electric field, and hence we can create the net dipole moment. And the substances which is holding true for all these assumptions, we call them as linear isotropic dielectrics. Now let's move on to electric polarization. So what is the meaning of electric polarization? So the dipole moment per unit volume is called as electric polarization. We know that when a dielectric is placed in an external electric field, so we can observe there is a change in net dipole moment. So when a net dipole moment is developed along the dielectric, then the dielectric is said to be polarized. So that is P is equal to chi E into E. So what is the term chi E here? It's a constant, and we call them as electric susceptibility of the dielectric medium. So what is P here? It's an electric polarization, and E is nothing but an electric field. So basically electric polarization is nothing but the dipole moment per unit volume. These are the few important terminologies and the topics to be understood in the study of electrostatic potential and capacitance. In the next session, let us learn some more interesting concepts. Until then, keep learning all of you. See you all. Thank you.